start off, give a recap of internal flow, and then keep talking about what we haven't finished with internal flow yet. Do you all have any questions about anything for the lab, anything we covered recently?
Is there any way we could shift the date to Wednesday so that last minute questions can be asked
Because we don't have
yeah.
class on Monday. That's a good point. And we have a lot of office hours on Tuesday, don't we? Sure, let's do that. We'll make the lab due on Wednesday since Monday is a holiday, so you don't have office hours. So we have a lot of office hours on Tuesday, and I'll shift mine from Monday to Tuesday. All you gotta do is ask, right? Just ask. All right, so lab due on Wednesday, and then no class Monday. On Tuesday, we'll have recitation, talk about some internal flow problems, maybe some more first law problems. Can never get tired of those. And then start back on Wednesday with lecture and lab due Wednesday. I will update that on Canvas. Okay. All right, yes.
Is the homework also due Wednesday?
Homework is due Wednesday. Yeah, I'm not pushing that back. Because I'll have another homework assigned on Wednesday, right? So, yeah. Okay. So we finished talking about, on Wednesday, we finished up class with talking about internal flow in the entry region. So basically we said for the velocity boundary layer and the thermal boundary layer, they both develop as soon as they start entering the pipe. They start developing this entry region, then the boundary layers merge. When they merge, the boundary layers become fully developed, and you have different expressions for the Nusselt number depending on if you're in the fully developed region or the entry region. So the fully developed region, we said H is a constant in fully developed flow. So the Nusselt number is going to be one of these two constant values depending on the boundary condition, if it's a constant surface heat flux or a constant surface temperature. And because the fully developed region is going to be preceded by an entry region, you're typically just going to be looking at local values of the Nusselt number in the fully developed region. Does that make sense? So you're going to typically have entry region and fully developed region. So if you're wanting to look at average values, you're going to have to consider both regions. But if you're just looking at local values in the fully developed region, they're these constant values. And then for internal flow, for these correlations at least, you evaluate fluid properties at the mean temperature. So typically, since we're only looking at local values, it's just the local mean temperature at that X location. If for some reason you wanted to evaluate an average just over the fully developed condition, then you would use the average mean temperature of kind of whatever you were considering your inlet and your outlet position to be. And then we started talking about the entry region, and there are two different kind of problems associated with that. So you can have a thermally developing boundary layer that occurs in the presence of a fully developed velocity boundary layer. And that occurs if you have an unheated starting length, so there's no heat transfer, and you just have the velocity boundary layer developing initially. It becomes pretty well fully developed, and then the thermal boundary layer starts developing in the presence of a fully developed velocity boundary layer. Or it can occur for oils, where the velocity boundary layer develops much more quickly than the thermal boundary layer. So for that problem, for the constant surface temperature boundary condition, we have an expression for the average Nusselt number. So again, entry region, evaluating the average Nusselt number over typically an area that includes the entry region and the fully developed region. And then for the combined entry length problem, so both of the boundary layers are developing at once, we have another expression for the average Nusselt number for a constant surface temperature. And I have like 2 more equations to write on this, so I'll just finish it out on these notes and then swap to the next day. So for the combined entry length problem with a constant surface temperature, the average Nusselt number, let's write that out. This one requires a lot of space. 3.66 over the hyperbolic tangent of 2.264 times the Gratz number plus 1.7 times the Gratz number to the negative 2/3. And here Gratz numbers to the negative 1/3. Plus 0.0499 Gratz number times the hyperbolic tangent of the inverse Gratz number. And all of that is over hyperbolic tangent 2.432 Prandtl number to the 1/6, Gratz number to the negative 1/6. And that is for Prandtl number of greater than approximately equal to 0.1. Okay. Make sure I have that written down correctly. And then we said for the average Nusselt number in internal flow, fluid properties are evaluated at the average mean temperature and that is mean temperature over bar. And that's just the average of the mean temperature at whatever you're considering your outlet to be or your initial location, and the mean temperature or the inlet and the outlet. So whatever you're considering your first and last locations to be, it's the average of the mean temperatures at that location, those 2 locations. So we have entry length problems, thermal entry length, combined entry length, and we have expressions for the Nusselt number for constant surface temperature for both of those. We do not have expressions for the constant surface heat flux for those, and we'll talk about why in a little bit, but basically because you can calculate H from other equations. So you don't need to calculate the Nusselt number to calculate H, or the average H for a constant surface heat flux. So we only have these expressions for the average Nusselt number for the constant surface temperature. All right, questions on any of this? Yeah. Oh yeah, I didn't close that, did I? Is that what you're asking?
Yeah.
Yeah, so parentheses around the entire thing. Hyperbolic tangent of the entire thing. Hugh, did you have a question?
Yeah, but when you say 4T sub, what does that say? In your bottom line there, is 4 something in the internal flow?
Oh, average Nusselt number.
Oh.
Yep.
Oh, okay.
Everything else clear? Okay. All right, so move these out of the way, and
One other thing.
yeah,
For the, at the bottom, for the average incident number, is that the GZ to the negative 1/5 or negative 1/6?
negative 1/6. Yeah, sorry, my pencil keeps breaking. Just make that a little more clear. Negative 1/6. 1/6 and negative 1/6. Okay, good. All right, so let's talk about appropriate use for these different expressions. Okay, let's talk about the entry region. So there will always be a velocity entry region. So the boundary layer development is caused by the fact that you have, zero velocity at the surface and a finite velocity of the fluid. So you'll always have a velocity entry region. And there will be a thermal entry region if the fluid and the surface are at different temperatures. Which will frequently be the case. So there's a thermal entry region if there's a delta T between the fluid and surface. The fully developed expressions like we said, those fully developed expressions can be used to calculate the local or the average values in the fully developed region only. And then the entry region expressions are used to calculate average values over a length of the pipe that includes the entry region and the fully developed region. And again, we only have expressions for a constant surface temperature. Boundary condition for the average values over the entry region and the fully developed region. And that's because the constant heat flux boundary condition, you don't need the Nusselt number to calculate H. So when should you use the thermal entry length versus the combined entry length expressions? So if the velocity entry length is much smaller than the thermal entry length, and this will only be true, so we'll only use this thermal entry length expression for unheated starting lengths or for oils. So if you have a internal flow problem, it's always still good to calculate both the velocity entry length and the thermal entry length and kind of compare them. But for unheated starting length or for oils, you'll typically find that the velocity entry length is kind of orders of magnitude smaller than the thermal entry length, and it'll be apparent that you can use the thermal entry length expression. So for these two cases. Otherwise, we'll use the combined entry length expression. So we said there's no entry region expression for the constant surface heat flux. So we'll talk about how you can calculate H for that. So no entry region expression for constant surface heat flux. Calculate H, instead you use the simplified steady flow thermal energy equation. So what we introduced, I think on Monday or Wednesday, Q dot is m dot Cp times the mean temperature at the outlet minus the mean temperature at the inlet. And we basically said that this right-hand side, this m dot CPT, is the rate of thermal energy being advected past a given cross-section. And if you subtract m dot CPT at the outlet minus m dot CPT at the inlet, that's going to tell you the rate of thermal energy advection, how that rate has decreased between the inlet and the outlet. And that's going to have to equal the amount of heat that was either input to the pipe or lost from the pipe, or to the fluid in the pipe. Yeah.
You said that was Q dot.
This is Q.
Oh, okay.
Yeah. So this is heat rate. So we drew a little energy balance around a differential element in a pipe and said that the heat transfer going into or out of the pipe is going to be equal to this quantity here. And if we neglect radiation, so if radiation and axial conduction are negligible, then this Q is going to be only due to convection alone. That's the only mode of heat transfer that could be occurring in or out of the fluid in the pipe. And therefore, the m dot Cp T at the outlet minus T at the inlet, this expression, is going to be equal to the convection rate equation. So if the heat transfer out is due only to convection, then this heat transfer rate is going to be equal to the convection heat transfer rate. And then H, you can just solve that for m dot C sub P times the mean temperature at the outlet minus the mean temperature at the inlet over A times Ts minus T infinity. And so this is for how to solve for H for a constant surface heat flux, because we don't have expressions for the Nusselt number. And this is typically going to be average H. We do have expressions for local H in the fully developed region for both boundary conditions. So this is just calculating average H that includes the entry region. So if we're calculating average H, then this surface temperature is going to need to be some sort of average value of the surface temperature. Because for a constant surface heat flux, the surface temperature is changing, but it's changing linearly with x. So this Ts is the average at the inlet and outlet. So this is again, the mean fluid temperature at the outlet, the mean fluid temperature at the inlet across the cross section of the fluid inside the pipe. And then this is the average surface temperature between the inlet and the outlet. So the surface temperature of the pipe. Okay. Questions on that so far? All right. And just to make sure we understand the distinction, so if you had a constant surface temperature and you were evaluating the convection rate equation for that, the surface temperature is just T sub S, it's constant, so you don't have to worry about taking the average. So you kind of have to think about what your boundary condition is and how that affects all the different temperatures and how they change with X. Okay. Let's talk about temperature dependence of the fluid properties. So we said for internal flow, we typically evaluate the fluid properties at the mean temperature of the fluid inside the pipe, as opposed to external flow, where it's the film temperature. But for liquids, the viscosity typically changes significantly with even small changes in temperature. So you can have variations in the viscosity really close to the surface that are not accounted for if you have fluid properties evaluated at the mean temperature, and the mean temperature and the surface temperature are somewhat significantly different. So we're just going to say anytime you're using liquids, we'll correct the Nusselt number expressions. So this is if it's water or oil or something inside the pipe rather than air or another type of gas. So for liquids, we can correct the Nusselt number expressions. By multiplying the expressions by this factor that we've seen before in some of our empirical correlations of the dynamic viscosity divided by the dynamic viscosity evaluated at the surface temperature raised to the 0.14. And here, mu is evaluated at the mean temperature. Mu and all of the rest of the fluid properties are evaluated at either the mean temperature or the average mean temperature, depending on if it's a local or an average correlation. And mu sub s is evaluated at the surface temperature or the mean surface temperature. So we'll say this accounts for viscosity variations. And this correction is just going to apply to our Nusselt number expressions for a laminar flow of liquids in a circular tube, which is the only type of tube we're going to talk about. So all those Nusselt number expressions that we wrote down, if you're using a liquid, you need to multiply them by this correction factor. Okay, questions so far? All right, let's talk about turbulent flow. So everything we talked about previously, all the expressions we wrote down were for laminar flow. So for turbulent flow, it's a little bit simpler. So again, we have fully developed region and entry region. So we'll talk about those separately. So for fully developed region, and these expressions are only going to be for smooth tubes. So surface roughness can change the expressions for the Nusselt number. And you can, there's like some expressions that incorporate the surface roughness factor, and you can look it up on the Moody diagram, but we're only going to talk about the expression for smooth tubes. With either boundary condition, so with constant surface heat flux or constant surface temperature, the local expression for the Nusselt number. So remember, we're talking about fully developed region. It's going to be preceded by an entry region. So we'll just write down the expressions for the local Nusselt number in the fully developed region. So that's 0.027 times the Reynolds number to the 4/5 times the Prandtl number to the 1/3. And then for this expression, we'll have the correction factor for the viscosity variation for all fluids. And then this is applicable for Prandtl numbers between 0.7 and 16,000. Sorry, 16,700. Reynolds numbers greater than approximately 10,000. And this is just saying that our entry length in turbulent flow is approximately equal to 10 times the diameter. So you would use it if your length or your exposition of interest was greater than 10 times the diameter. And if you remember, we said that our Reynolds number expression, or our critical Reynolds number, is about 2300. You can use the laminar expressions, and then above 10,000 is the turbulent expressions. So between 2300 and 10,000 is kind of this transitional region where there's not very, like, good expressions for that region don't really exist. If you have a flow that is in that Reynolds number region, you can use the turbulent expressions. You just need to recognize that they will give you a larger error than if the Reynolds number is larger than 10,000. So let's write that down. We can use turbulent expressions for Reynolds numbers that are between 2,300 and 10,000. But they will have larger errors. Okay, the last situation is the entry region. So the entry region in turbulent flow is actually pretty easy to handle. So in turbulent flow, the entry region is typically pretty short, so we just ignore it. And we say, we'll just use the fully developed conditions for the entire tube. So in turbulent flow, entry length is fairly short. So the fully developed condition can be applied to the entire tube. In other words, the average Nusselt number is approximately equal to the local Nusselt number. And then for the local case, the only difference is the properties are going to be evaluated at the local mean temperature, just like before, except for mu sub s, which is at the surface temperature. And for the average, they're evaluated at the average mean temperature. Yeah.
Could you give a ballpark number for how much larger the airs are?
It depends on the fluid that you're talking about, and yeah, I really don't know. I don't think it even says in the book. Yeah, I think there would be a really wide range. Yeah. Any other questions? Yeah.
Is there a good explanation why the turbulent flow develops the boundary layer faster?
Yeah, so it's because in turbulent flow, you have more mixing, right? That's kind of typically what you associate with turbulent flow. And so it's going to be more, if you're just talking about the velocity boundary layer, you have kind of more momentum drawn from the free stream or kind of undisturbed flow into the boundary layer. So that increases the kind of boundary layer growth more quickly. Does that make sense? Kind of drawing in more momentum from the undisturbed flow. And then that's the same thing with the thermal entry length. Just more mixing, and you're kind of increasing the rate of heat transfer more quickly as well. Anything else? Okay. All right, so we've got a little bit of time left, and we kind of went through both external flow and internal flow without doing a whole lot of practice problems. We missed recitation because we had the exam. I did post recitation example problems for you all on Canvas for internal flow, and we did some external flow last week. But there's kind of like a lot of different situations and a lot of conditions for forced convection. So I wanted to go over just kind of a summary. So I wrote this up and I'll post it on Canvas, but I just kind of wanted to talk through it. You don't need to write any of this down unless you want to, because I'll post this on Canvas. So just kind of for external flow and internal flow, if you're posed with a forced convection problem, kind of where do you start thinking? Where can you start your problem solving, and then kind of what conditions do you need to consider? So basically right at the top, for all empirical correlations, you have to check the dimensionless parameter restrictions if they're applicable. So that's basically every time we wrote down an empirical correlation, we had like, oh, this is applicable for Reynolds number of this range, Prandtl number of this range, etc. So if those apply to the empirical correlation that you're interested in, you must check that the fluid properties, the dimensionless parameters, are within the range of that empirical correlation. Okay, so that applies to kind of everything. So first of all, if you have a forced convection problem, you should figure out if it's external flow or internal flow. It's going to be very different conditions. So for external flow, there are 3 situations that we considered. So we talked about a flat plate, we talked about a cylinder and cross flow, so flow moving perpendicular to the cylinder axis, and then we talked about a sphere, where the wake dynamics and the boundary layer development are similar to a cylinder and cross flow. So for the flat plate, we only talked about an isothermal flat plate, so that's constant temperature in space and time. And kind of the first thing you need to think about when you start analyzing a flat plate external flow problem is where the transition to turbulence occurs. So it's determined by this critical Reynolds number, and that corresponds to a critical X location. And that's 5 times 10 to the 5th for flat plate. And for the Reynolds number calculations for the flat plate, the characteristic velocity that you use is the upstream flow speed, and the characteristic length is either the X location of interest, if you're looking at a specific location on the plate, or if you're looking at the entire plate, that's the overall length. And then for these expressions, fluid properties are evaluated at the film temperature. In some cases, the surface temperature is what you'll be solving for, so you don't know the film temperature. And in general, if you're presented with that type of problem where you have to evaluate the fluid properties to figure out what the temperature is, but you need the temperature to know what the fluid properties are, you have to guess a temperature and then iterate. So the kind of 2 main conditions are if you have laminar flow or turbulent flow. In laminar flow, you can have expressions for local values of these parameters. We wrote down these expressions. And the restriction for that is the flow just has to be laminar at the location of interest. So you're just looking at a local value at one place, got to have laminar flow there. If it's an average value, then the flow has to be laminar over the entire region of interest. And we have expressions for the average friction coefficient and Nusselt number. Similar thing for turbulent. For local values, the turbulent flow just has to be turbulent at that location. And we have expressions for these local parameters. And then for average values, so now you're talking about over kind of a length of the pipe, the turbulent region is always going to be preceded by a laminar region. So we said if the flow transitions to turbulence right at the end of the pipe, or the tube, sorry, the flat plate, if the flow transitions to turbulence right at the end of the flat plate, then it's mostly laminar, and so you can use just the laminar average correlations. But if it transitions to turbulence before the very end of the plate, then you have to use the mixed boundary layer expressions, which give you average coefficients for the friction coefficient and the Nusselt number, those average values over the region that includes the laminar part and the turbulent part. Okay, we talked about a cylinder and cross flow. So here the Reynolds number is based on the diameter and the upstream flow speed. The Reynolds number influences where separation occurs, but you don't have specific laminar or turbulent regions that you have different expressions for. So all we have for this is one expression for the local value of the Nusselt number, which is valid only at that stagnation point at the very upstream position. And then we have an expression for the average value of the Nusselt number. And these depend on the Reynolds number. So that is where kind of the dependence on separation in the wake is incorporated into these expressions. So unlike the flow over a flat plate, you don't have to calculate a specific location and say, okay, if we transition to turbulence or not yet. You just have one expression, and the Reynolds number is incorporated into both of those to account for that. Okay, for the sphere, again, same thing. The Reynolds number influences where separation occurs. The characteristic velocity is upstream flow speed, characteristic length is the diameter, and we talked about two different conditions, solid spheres and freely falling liquid drops. So for solid spheres, we had an expression for the average Nusselt number, and for this is the first case where we had an empirical correlation where instead of evaluating properties of the film temperature, they're evaluated at the free stream temperature, except this mu sub s, which is evaluated at the surface temperature. And same as before, if they're unknown, you have to guess and then iterate. We also talked about freely falling liquid drops as kind of a special case, and we have a specific expression for the average Nusselt number for those. For this, the fluid properties are evaluated at the film temperature. Okay. Then we started talking about internal flow. So in internal flow, the transition to turbulence is determined by this critical Reynolds number, just like it is for flow over a flat plate. But the distinction is here, the Reynolds number is now based on the mean velocity inside the tube, which is constant for a constant mass flow rate, and the characteristic length is the diameter. So you'll have, so those are values that don't change with x, right? The diameter and the mean velocity. So you either have laminar flow or turbulent flow kind of entering the pipe. There's no transition to turbulence like you have for flow over a flat plate. But you still have to determine whether the flow is laminar or turbulent before starting the problem, because the expressions that you use for calculating the entry length and the Nusselt number and all those are different depending on if it's laminar or turbulent flow. So here fluid properties are evaluated at the mean temperature, which changes with x location. So the local parameters, anytime you have a local parameter, they're evaluated at the local mean temperature. If you have average parameters, they're evaluated at the average mean temperature. So that's the average of the mean temperature at the beginning and end of the region that you're considering. And the mean temperature, because it changes with x, we derived specific functions to calculate the mean temperature as a function of x for the two boundary conditions, constant surface heat flux and constant surface temperature. Okay, so that's kind of all Reynolds number calculations and figuring out whether it's a laminar or turbulent flow. And then for laminar flow, we just talked about today, for liquids, the expressions that we wrote down must be corrected for temperature variations by this mu over mu sub s correction. And then fluid properties evaluated at the mean temperature, except mu sub s, which is evaluated at the surface temperature. So for laminar flow, we have local values and average values, and those kind of correspond to our fully developed or entry region. So for local values, we only have expressions for local values in the fully developed region. And that's because if you want an average value, the fully developed region is going to be preceded by an entry region. So you have to account for both of those areas. So for local values in the fully developed region, we have expressions for the local friction coefficient and the local Nusselt number for the two different boundary conditions. And then average values, which include the entry region. We have, so you can calculate the hydrodynamic and thermal entry region lengths by this X, F, D, H, and T. And that can help you determine if the entry region is a thermal entry length problem or a combined entry length problem. So what the relative kind of entry lengths for the two different boundary layers are. So for the average values, including the entry length, we have the two different boundary conditions, the constant surface temperature, and we have an expression for the thermal entry length and the combined entry length, and then constant surface heat flux. There's not an expression for the Nusselt number, the average Nusselt number, because the average H we showed can be determined from the simplified steady flow thermal energy equation and the convection rate equation, combining those and calculating H from that. And then finally, the last situation we have is turbulent flow in a circular tube. So again, the local values from the fully developed location, expressions for local friction coefficient and Nusselt number, and then the average values, which include the entry region. And again, you can calculate the entry length of both the thermal and velocity boundary layers. And those are different expressions than the entry length for laminar flow. But in turbulent flow, the entry region is typically short and can be neglected, so you can use the same expression for average and local values in turbulent flow. Okay, so that's kind of a quick overview. I'll post this on Canvas, so if you're having trouble getting started, you can maybe use it as kind of like a little bit of a checklist for how to go through a problem. Do you guys have any questions? Yeah.
I don't have a question, but I do have feedback. Like, this is super helpful.
Thanks.
Like the summary at the end
Good.
really ties it all together.
Thanks. Yeah, I have gone through your midterm evaluations or your mid-quarter assessments, and I'll talk a little bit more about that on Monday, but this was good feedback, and this was kind of in response to saying like, hey, we need more guidance on how to work problems. So here you go. Hopefully it helps for the homework.
Sweet. Thank you.
Thank you.